So Suresh, is the screen visible, Suresh?
Yeah, visible, sir.
Okay. Uh, so Verilog HDL. So we have seen yesterday. So what is HDL? So HDL stands for Hardware Description Language. Okay. So if you want to go for the designing of digital circuits, so there are few traditional methods available. So few traditional methods are available. So these are the few traditional methods. So that is the gate level design and the schematic design. Okay. So if you want to construct any digital circuit, so you can construct the digital circuit by using the basic logic gates. Okay. So and also you can go for the schematic of the same thing. So you can go for the implementation in the transistor level or implementation in the gate level. So but by using these traditional design approaches, the complexity of the circuit becomes very high. So that creates a lot of the problem. Okay, so if there are more than 20 gates in a schematic or in a gate level design, what happens is that the circuit looks very clumsy and it is difficult for us to find any wire or something. So if there is anything error or there is any disconnection, if there are more than 20 odd gates, so it is very difficult for us to find out. So there are many disadvantages with this traditional methods. So here, where is the problem here? So nowadays the system specification. Okay, so if you want to design any project, the system specification is behavioral. So we are not defining the internal architecture of a system. So we are defining its behavior. We are defining only its behavior. So for example, if I want to go for some ALU here, so if I want to go for the design of ALU, so we will specify. So what are the arithmetic and what are the logical operations carried out by that ALU. So but we will not discuss the internal architecture of that ALU. Okay, so this is the system specific. So here, okay, sorry. So here what happened is that, so we are only defining the system specification. So that too, so we are just telling the customers or telling the others, so how the system behaves. So if you are giving these inputs and what are the outputs we are expected, so we are only defining that. So the internal architecture, everything we are not looking. Okay, so that is the one of the problem. So that is the one of the problems. So why we are going for the HDL. Okay. So the next one is manual translation of design in Boolean equation. Okay. So whenever if you want to get the optimized circuit, so what we are doing is that in the olden days, so we used to manually translate the design into Boolean equations, and then we are able to optimize that manually. So this takes a lot of time. Okay. So and next one is the handling of large complex designs. Okay, so you can do this. Okay, so traditional method or using of manual translation of designing in Boolean equations, everything can be done for the smaller gates. But when you are coming from the large complex designs, okay, what is happening is that, so we cannot handle that. Why? Because as the number of gates increases, the complexity will increase. Okay, and moreover, uh, so using of spice code. Okay, so normally for the analog circuits, what happens is that, so if you are drafting the schematic for any circuit, so that may be analog circuit or that may be a digital circuit. Okay, so in the multisim software or mental graphics or cadence or synopsys, so in any schematic based software. Okay, if you draft the schematic and if you run the schematic bins, so you get the simulation. But the circuit what we have drawn, that circuit will be converted into the spice code. Okay, so spice means simulation program for integrated circuit emphasis. Okay, so the circuit will be converted into the spice code, but we cannot use the spice code for all the circuits. Why? Because if you want to use the spice codes, we have to need the libraries. So we have to need the libraries at which technology we are running. So there is a lot of process into it. Okay, so it is very difficult to write the spice coding also. So these are the various problems that are faced normally. So these problems have deviated us to define the HDL programming. So you can see the advancements over the years. So you can see the Intel 4004 processor here, so which was introduced in the year 1971. So here there are 2300 transistors were present on this IC. So the frequency of the processor is 108 kilohertz, and whereas the Intel P4 processor, which was introduced in the year 2000, so it has 40 million transistors. Okay, and the operating speed of this frequency is 1.5 gigahertz. So you can imagine how many number of transistors are fabricated in the given small area. So the number of transistors that were fabricated in the given area were increased. So even Moore's law failed to denote that. Okay, the so in order to do this many number of gates or this many number of transistors, so you cannot directly do it manually. So you need some other programming language. Okay, so in order to overcome all these problems here, so we are going for the use of HDL language. Okay, so HDL is a language so that describes the hardware of a digital systems in a textual form. Okay, so whatever the digital system is there, so that digital system behavior is described in the form of a text. Okay, so we are writing that the behavior of a digital system or the architecture of the digital system in the form of a program, so which is nothing but a textual form. Okay, so it is a device independent representation. Okay, so the HDL programming is a device independent representation. So if you are writing the program for APCA, it is the same program. If you are writing the program for ASIC, it is the same program. So if you are writing the program for Xilinx APCA, it is the same program. If you are writing the program for Ultra APCA, it is the same program. So it does not depend upon the target what you are using. Okay, so it is independent. The next one is, so it resembles a programming language, but is specifically oriented to describing the hardware structures and behaviors. Okay, so HDL is a programming language, but the main intention of this HDL program is that, so the main intention is to describe the hardware structures. So it describes the hardware that is present in the digital system. So what are the connections? Different connections are given here. So what are the different logic gates and what are their connections? How they behave? So all these hardware structures and behaviors are described by using the HDL language. And moreover, the main difference between the traditional programming language and the HDL programming language is that the traditional programming language represents the serial operations. That means if you are writing the program, so the traditional programming language, what it do is that, so it will execute line by line. Okay, if there are 10 lines in the program, means the normal programming languages will execute the first line. So after that second line, after the third line, so like this. So serial execution will be there. But in case of the HDL program, the execution of the program will be parallel. So in parallel, the program will be executed. So why we are going for the HDL program is the main important use or the most common use or the main motto of HDL program is to provide the alternative to the schematics. Okay, so instead of drawing the schematics, so we are going for writing the program. So if you want to draw the schematic, means it is very difficult. For example, so if I want to design an ALU, okay, so if ALU, so which does the addition operation, subtraction operation. So after that, which does the logical operations like XOR and bitwise operations. Okay, so bitwise and operations, for example. So if I want to do this, so how many number of gates I have to use? Okay, for adder I have to use, for a single adder I have to use the one XOR, normally two XOR gates, and I have to use one OR gate and two AND gates like that. I have to use for each and every adder. So if you are constructing that by using the gates, so the circuit becomes very difficult. Okay, so in order to provide a common alternative, or in order to provide a better solution other than drawing the schematics, so we are using the HDL program. So the next one is when a language is used for the above purposes. Okay, so instead of schematics, okay, instead of schematic, if you are using the HDL program, so this program, HDL program, is referred to as the structural description. Okay, so in the structural description, so what it does is that, so it will describes the interconnection of various components. So normally what happens is that, so when you are writing the HDL program, that may be VLSI or Verilog, so we have various types of writing the program. So various type of describing the program. So normally there will be behavioral modeling, structural modeling, so as well as the data flow modeling. So these are the different types of modelings, so which we find in the HDL. Okay, so the best alternative to the schematic is the structural description. So in the structural description of an HDL program means, so here we will define what are the components that are used in the architecture. Okay, so we will define the components used in the architecture, and also we will define the interconnections between this architecture. So this is known as the structural description. So behavioral description means, so what we do means, so we will define what are the inputs and what are the outputs, and what is the relationship between the input and output. So based on the relationship, how you get the output. So this will be defined in the behavioral description of a program. So in the data flow program, so how the data is flowing from the inputs to outputs by using various data manipulating equations. That what you describe in the data flow. So this in detail you can see later on. Okay, next. So whenever we are going for the structural description, so we are using the primitive components. Okay, so primitives means the predefined logic gates, or the predefined gates that were present in an HDL programming, they are called as primitive components. Okay, for example, if you take any HDL program, so the basic logic gates like AND, OR, XOR, XSTAR, okay, and universal gates like NAND, NOR, all this will be predefined. The functionality of these gates will be predefined in the HDL programming. Okay, so these are known as the primitive components. And moreover, so this representation of the HDL will be unique, and we can use it for the portable representation of the simulation input. Okay, so this is about the basic introduction of the HDL. So HDL, the important thing what we should know is that HDL is a language that describes the hardware of a digital systems, so in a textual form. So and moreover, it is a device independent representation, and so it is mainly used to specify the connections between the different circuits in a digital system, and also to define the behavior of the digital circuit. Okay, and moreover, here you can see the HDL can be used to represent logic diagrams, Boolean expressions, and other more complex digital circuits. Okay, so here by using HDL, so what we can do is that we can represent the logic diagram. So that means the gate level connections of the circuits and its corresponding Boolean expressions and other complex circuits. Okay, so here whenever we are going for the description of a HDL, so there will be a top-down design description or a bottom-up design description. So there is two types of description. Okay, so a top-down design description will be there, or bottom-to-up design description will be there. So what is meant by that means, so for example here, so I want to design a 4-bit triple carry adder. So if I want to design a 4-bit triple carry adder, what I require? So I require first 4 full adders. Okay, so and the interconnection. So in order to define the triple carry adder, so that I will draw the required 4 full adders I will take. So after that, so I will give the required interconnections to define the ripple carry adder. So after that, so whatever the full adder you have taken, so as a designer, we know that it is a full adder, but the person or the computer or the software which simulates your program doesn't know what is that, what is the full adder. So it is just a name. So again, we have to define the functionality of the full adder. So you can define the functionality of the full adder directly, or you can define the functionality of the full adder by using the half adders. Okay. So again, so after the full adder, next we get the half adder. So in the half adder, again we have to define the AND gates and OR gates. So like this, if you take a ripple carry adder, the top level description will be the ripple carry adder and its connections. After that, again we have to define what is full adder. After defining the full adder, again we have to define the what is half adder. So after defining the half adders, next we have to define the what is XOR gate and what is AND gate and what is what is AND gate. So this we have to describe. So that is the top down design. So similarly, we have the bottom up design. So where we will start from the lower end. So first we will define the functionality of the logic gates. Okay. So after that, from this we will define the half adder. From the half adder we define the full adder. So by using the full adder, we define the ripple carry adder. Okay. So these 2 types of designs we can use: top down design or the bottom up design. So normally what happens is that top down design will be used. Why? Because it is a very high level description of the entire system. So from the system top, so we will get the details up to the bottom. Okay. So normally, so we will go for the top down design. Okay. So if you are using HDL means, so you can go for either top down or bottom to up. So depending upon your ideology and depending upon your comfortableness, so you can go for anything. So the next one is one more reason. So the one more reason why we are going for the HDL program is that, so the major reason is because of the logic synthesis. Okay. So the major reason why we are going for the growth of use of HDL is so logic synthesis. So what is meant by logic synthesis? So logic synthesis means conversion of your HDL program into the netlist. Okay. So as a documented language, so as a textual language, so HDL is used to represent and document. So to represent and document the digital systems in the form that can be read both by the computers as well as by the humans. So what happens is that, so if you are writing the HDL program, that can be understood by the humans. So who knows programming, so they can understand. But when when we are simulating it, so the computers doesn't understand what is HDL language. Okay, so it has to be converted into the target primitives. The HDL has the capability. Okay. So by using the softwares, the HDL has the capability of converting your high-level programming language into the system understandable language. Okay, so which is nothing but the process is known as the logic synthesis. Okay, so logic synthesis means conversion of HDL program into the netlist. So which we have discussed yesterday. So where netlist is nothing but the connection of various logic gates and the internal connections. Okay. Next, whatever the HDL program you are writing, the content of this HDL program can be easily stored in the computer, and we can retrieve the program whenever necessary, and we can again resimulate it by using the software which we require. Okay, so it is one more importance of HDL language. Okay, so after writing the program, we can store the same program in the computer in the same software where we have simulated. Okay. So again, after any number of days, you can retry the same program and you can process it by using the EDA software, and we can use it for the further purpose. And moreover, so the basic applications of HDL processing are simulation and synthesis. Okay, so the simulation means synthesis. This we have seen already. So next day. the advantages of HDL. Okay, so these are the few advantages of HDL here. So the first one is from the behavior to implementation. So if we are talking about the digital systems, so from the designing of your digital system, and after that, the from the behavior of the digital system to the implementation of digital system can be done at various levels of abstraction here. So normally what happens is that if you want to design a digital system, so first the circuit, the designs will be done at various levels. The lower level designing is done at the transistor level. Okay, so by using the CMOS transistor, that is the PMOS, NMOS, and CMOS transistor. So we will be we will build normally the gates, so logic gates. Okay, so next, this is the lower level of the abstraction. Okay, so that is the first level and lower level of the abstraction, where we are going for the circuit level description. Okay, so after the circuit level description, the next type of description is the gate level description. Okay, so in the gate level description, what you will do is that, so by using the different predefined gates, or by using the gates which we are defined by the designers, so we will construct the circuit by using the gates. So but the problem with the circuit level design and the gate level design is that when the number of transistors or when the number of gates are more, so the circuit will be more complex. So after that, the next level of abstraction is the data flow. Okay, so in the data flow, what we can see is that, so from the inputs to outputs, how the data is manipulated from the inputs to the outputs by using the data manipulating equations. Okay, or by using the Boolean expressions, or by using the Boolean equations. So by using the Boolean equations, how the data is transferred from the input to the output. So that we can see it in the data flow. And the last and the higher level of abstraction is nothing but the behavioral level. So where you will be using the dense programming structures, and you will be writing the program without knowing the knowing the internal architecture. So just we will use the relationship between the input and output, and we will get the outputs based on the input parameters. So the HDL, what it does is that it allows the designers to talk about the hardware at each and every level of the abstraction. Okay, so you can the designers can discuss the circuit level implementation of the design. So the designers can also implement, or they can also discuss about the gate level implementation of the circuit. They can also describe the behavioral level. They can also describe the data flow level. So the designers will get the opportunity to discuss the circuit or design the circuit at any level of abstraction. Okay, so that is one of the major advantage of HDL programming. So if you are going for the spice code, what happens is that if you are going for the spice code, means you cannot describe at various levels. So only at the transistor level and their interconnections only you can describe in the spice code, but you cannot describe it in the behavioral level or in the data flow level. So that is the disadvantage of the spice code, and it is the advantages of the HDL program. Next, the designers can develop an executable functional specification that documents the exact behavior of all the components and their interfaces. So that means the designers can able to get a executable functional specifications. Okay, so if you are going for the implementation of your program on the PCA, so you can get the .bit file. Okay, so this .bit file, when you are implementing it in the FPGA, it will gives us the total behavior of your components and also its interface. Similarly, you can document that also. So the designers can make decision about the cost, performance, power, and the area earlier in the design process. Okay, so it is very important here. Okay, so when we are going for the design, so if you are getting the high power, okay, so the power consumption when you are simulating the initial stages, if you are getting the high power consumption, so designers has the time to rethink about the designing issues. So if you vary what design parameters, how the power can be reduced, and moreover, the next important criteria is area. Okay, so the designers have the chance to reduce the area of the circuit, so they can design in the other ways. They can design the digital system in the other ways so that the area of the implementation will be reduced. Okay, so by using the HDL program, it is one of the advantage. Okay, so what you can do is that, so whenever we are writing HDL program and if you are going for the implementation in the any one of the software, so you can get the power values, area values. So if you are not getting the good values, means you can go back to the designing, you can make the changes in the designing, again you can rewrite the HDL program, and again you can resimulate and resynthesize. Okay, so that it is one of the advantage. And one more important advantage of HDL program is that, so whatever the program done, or whatever the program created or designed by the designers, so can be automatically tested. Okay, so there are different softwares, so like model sim for Pestasim for mental graphics, NC sim from Cadence. Okay, so Vivado from Xilinx. By using these different EDA tools, so the verification engineers so can verify the functionality of the code, and if there is anything fault in the code, so they can easily manipulate the design for the verification synthesis, and they can go for the optimized output. So yeah, so this is the thing we have discussed already. So the higher level HDL programming abstraction levels. Okay, so it is the higher level of abstraction here. Okay, higher level of abstraction here. Okay, this is the behavioral
Sir,
level. Hello.
sir, sir, what is meant by abstraction?
So abstraction means, so it is the different stages. Okay, so different stages at which we can work.
Okay, okay. Thank you, sir.
Okay. So the first higher level where you can work by using the behavioral is nothing, by using the HDL is nothing but the behavioral level. Okay. In the behavioral level, how you work means, so whatever the design is there, so the design algorithm will be implemented. Okay. So design algorithm will be implemented with the little concern for the actual hardware. So here they will not see what is the hardware we are using. Okay, so they are least bothered about the hardware they are using in the design. So but these will be implemented by using only the high level algorithms. Okay, and the next one is data flow. So data flow means, so here the design is implemented by specifying how the data flows between the registers. So that is from the inputs to the outputs. Okay, so in order to store the data, we will be using the registers. Okay, so how the data will be moving from the inputs to outputs by using the data manipulating equations. And the next one is gate level. So here the design or the module will be implemented only in the terms of logic gates. So logic gates and the universal gates, that is AND gate, OR gate, NOT, NAND, NOR. Okay, so and their interconnections. So there is one more level of abstraction normally that we don't use in the HDL. So that is the circuit level description. Okay, so where these AND gates, OR gates are also designed by using the PMOS and NMOS transistors. So which one to use? Okay, so here we have got majorly 3 HDL abstraction levels. So among these, so which one is the better to use? So you will get the doubt. So whether we have to go for the behavioral level, or whether you have to go for the data flow level, or whether you have to go for the gate level. So when you in one particular abstraction or in one particular triple carry adder. So if you are going for the 4-bit triple carry adder, means what happens? So first you will take 4 full adders. After taking the 4 full adders, you will describe the internal connections. Okay, so in the connections between these full adders. Okay, so this looks like the structural program, nothing but the gate level program. So where you take the full adder and you will define its internal structures. Okay, so after that again you need to define what is full adder. So this full adder you can define directly in the behavioral level, so by using the or in the data flow level, so directly by using the equation S sum is equal to A XR B XR B XR C, and carry is equal to AB plus BC plus C. So directly you can define that. Okay, if you want again go for the structural means, again you have to describe. So full adder, it is the combination of two half adders. Again half adder, we have a few more logic gates. So if we are using the same type means, okay, the same type of functionality means, what happens is that it may be little complex or it may be high in area. So more number of gates will take place. For example, here in the ripple carry adder, so if you describe in the each step about the internal connections means, more number of gates will happen. So once after getting the to the full adder designing, if you directly specify by using the equations means, it is very easy. So otherwise again we have to define the half adders again. All this stuff will be there. For example, if you go like this means, what happens, more number of gates will come. So for example, if you want to describe the functionality of the ripple carry adder in the behavioral model means, you have to write the algorithm. Okay, so again it will be quite complex for the learners or for the beginners or for the above beginners. Okay, so if you are expert means, you can directly write in a digital system. You are expert means you can directly write the ripple carry adder behavioral program. So otherwise it is very difficult. The complexity of writing the program increases. Okay, so that means depending upon the complexity and depending upon the requirements, that is the power, area, and delay, so we can mix all these architectures and we can get the best one out. So the next another important one is, as I told you, so the designers can use the automated tools, that is the EDA tools. So EDA tools means electronic design automation tools. So in order to synthesize a low level gate modeling. So this is the about the
Sir,
logic simulation. Hello.
sir, what is meant by low level gate modeling?
Low level gate modeling means, so whatever the circuit is there, so conversion of that circuit into the gate level. So by using the basic gates like AND gate, OR gate, and NOR gate. The circuit consists of only AND or NOT gates. That's all.
Okay, sir. Okay. Thank you, sir.
Okay. So next one is the logic simulation here. So which we have discussed yesterday. So logic simulation means, so it represents how the structure and the behavior of digital logic system will be present. So when you are using through a computer aided software here, okay, a simulator, what it does is that, so it will interpret the HDL program and it will produce a readable output. So that readable output may be a timing diagram, or in some of the HDL programs, there is an option of getting the outputs to be printed. Okay, so the simulator will give all these options. So it will interpret the HDL description and produces a readable output. So that output may be in terms of the values or in terms of the timing diagram here. Okay, so this will be done before actually going for the fabrication. And one more thing is that by doing the simulation, we can be able to find out the logical errors. Okay, so the syntax errors can be found before doing the simulation. We can find out the syntax errors. Okay, but the logical errors, the designing errors, that can be found only during the simulation. Okay, so these logical errors can be detected, and these can be erased by using this logical simulation. The next one is, errors detected during simulation can be corrected and modified by the appropriate HDL statements. So that means whatever the logical errors we are getting, so this can be found out and we can correct the changes as required. And the next important thing is that normally what happens is that, for example, if I am going for the AND gate, okay, if I am going for the AND gate means what happens? So AND gate has two inputs. So two inputs means, so we have to give the 2 to the power of 2. That is the 4 input patterns. So 0, 0, 0, 1, 1, 0, and 1, 1. So normally in the academics we have a practice of forcing the values in the model sim or in the Xilinx ISC or some other tools. What we will do is that, so after checking the syntax, we will directly go for the simulation. In the simulation, we will force the values. So A is equal to 0, B is equal to 0, simulate it, you will check the waveform. Okay. So other than that, so we can write a program for the testing of your design. So that program is called as test bench program. The stimulus that tests the functionality of the design is called a test bench. So whatever the inputs you are giving, you want to give to your design, so that inputs or that input values can be written in the form of a program. So that program is called as the test bench program. Okay. So in order to simulate a digital design system, the first thing is that, so we have to describe the design in the HDL language. Later on, the second thing is that we have to verify the design by writing a test bench waveform. Okay, so by writing a test bench program, you can verify the output. So these test bench program can also be written in terms of the HDL language. Okay, so this we have seen about the logic synthesis. So it is the important part of the logic synthesis. So when you are writing the HDL description, so first what happens is that, so the HDL program will be translated into the intermediate representation, so which is nothing but the Boolean expression. So here we will give the area constraints, delay constraints, and the technology library. So based on these input constraints, so these unoptimized Boolean expressions will be made to the optimized Boolean expression. So that means in the Boolean expressions what you are getting, so if there is any redundancy means, so that will be minimized. So this how you can convert the pre-optimized Boolean expressions to optimized Boolean expressions.
Sir, excuse me, sir. Sir, redundancy means repetition of values, right?
Yeah, unwanted terms.
Okay, sir.
So,
Okay. Thank you, sir.
And the technology mapping. So technology mapping means the important thing is that, for example, in the FPGA, if you take, so there will be LUTs. So CLBs will be there, configurable logic blocks. In the configurable logic blocks, there will be LUTs. So there are a few number of LUTs in a FPGA. So after in order to dump the program, you should know how many LUTs are there in your FPGA and how many LUTs will be occupied by your program. That's we should know. Why? Because if the number of LUTs required by your program are more than the number of LUTs present in the FPGA, means you cannot implement that program on the FPGA. So that is the reason why technology mapping is very important. So in the technology mapping, what it does is that, so as per the requirement of your target primitive, so the software which you are using, it will give us so how many LUTs are required for your program implementation. So what will be the critical path? So critical path means the longest delay present. Okay, so all these parameters will be given in the technology mapping. So based on that, if you want to make any changes, you can make. So then the final netlist we get here. So the next one is the history of HDL program. So the HDL program is a simple, intuitive, and effective way of describing the digital circuits. It was first developed in the year 1984 to 1985 by Philip Murby. Okay, so in 1990, Cadence opened the language to the public. So from the particular Philip Murby, the Cadence has overtaken it, and they had made open for the public. And in the year 1995, so IEEE has standardized the language. So as we know, there are two types of languages. So one, they are Verilog HDL and the VHDL. So let us see the basic differences here. So the name is Verilog HDL. So who is making that any changes or anything for this means, so you can tell him as the coach. Okay, so open Verilog International. So www.ovi.org. So it is the company, so that is making the changes and debugging anything are present in the Verilog HDL. Okay, so what is the importance of this Verilog HDL is that, so it has a very good acceptance in the ASIC. So if you want to go for the implementation of application specific integrated circuit, the Verilog HDL is accepted more. Okay, and moreover, at lower level designs, so Verilog HDL will be used. One important thing is that the results, the simulations in the Verilog HDL is very fast when compared with the VHDL. Okay, so next, the designing of Verilog is the programming writing using the Verilog is very simple when compared with the VHDL. Why? Because so it is used, it is developed from the C language. Okay. So, but in short, if you know the C language properly means, so you can easily learn the Verilog without any disturbances. So the people in the North America, Asia, Japan, especially among the industrial supporters, so Verilog HDL will be used. So Verilog HDL will not be used in the not popular in the Europe. So this is about the Verilog HDL. So if you take the VHDL, so the VHDL is maintained by VHDL International. So its website is www.vhdl.org. The important characteristics of VHDL is that, so when you are going for the lower level designs, okay, so VHDL is very weak. But if you are designing the high level and security level designs means, so VHDL is very superior than the Verilog HDL. And moreover, the results, the simulation results, so we will be getting very slower in VHDL when compared with the Verilog. Okay, so in order to overcome this, VHDL is constantly improving and it wants to give a tough fight to the Verilog. Okay, so and moreover, this VHDL is very popular in academics. So and this VHDL is made especially used in the Europe. Okay, but significant number will be used in US and Canada. But in Japan, it is disliked in Japan, but it is gaining the popularity worldwide. Okay, so these are the basic differences between the Verilog and the VHDL. So as our workshop is on Verilog, so now let us focus into the Verilog. So let us see what is the popularity of Verilog. So Verilog HDL. So it is a general purpose HDL programming language. That means you can design any digital system. It is very easy to learn and it is very easy to use. And moreover, the syntaxes of Verilog HDL resembles the syntaxes of C language. Okay, so as most of the engineering students will learn C language in their engineering first year, so the students can easily adapt to the Verilog HDL very easily. So when compared with the VHDL, okay, and moreover, the designers can able to design your program at any level of abstraction. Okay, and also Verilog gives us the flexibility to combine the different levels of writing the program, so as intended by the designer. And moreover, so Verilog HDL is supported by the most popular synthesis and simulation tools. So almost all the EDA tools in the world so will accept the Verilog HDL. Okay, and the important thing is that, so after the synthesis, okay, so after the synthesis, if you want to do the simulation with respect to the technology, all the fabrication units in the world, so all the fabrication units in the world will give the technology files. That technology files can be adapted easily to the Verilog HDL. So for example, if I want to use the 45 nanometer technology means I cannot directly make the size of the transistors 45 nanometer technology. So I have to get the library files from the fabrication units. Okay, so these library files what I get from the fabrication unit will be can be adapted easily by the Verilog HDL when compared with the VHDL. And one thing is use of the PLI, that is the programming language interface. So we can easily interface this Verilog HDL to the simulators as per the designer needs. So this is the few important points why the Verilog is gaining the popularity when compared with the VHDL. Okay. So next, what are the trends? So what are the trends that are there at present in the HDLs? So whether it may be a VHDL or whether it may be a Verilog HDL, the designs can be done at the behavioral level. So there are formal verification techniques. Okay. So there are formal verification techniques in the HDL. Okay. So that maybe if you are coming from the simulation, as I told you, if I want to simulate something with the 4 inputs, means I will get the 16 input parameters. Okay. So for example, here, let me tell you a simple example. Uh, Take a full adder. If you take a full adder, so after taking the full adder, what happens is that, so the output of the full adder is A XR, B XR, C. So next, carry is equal to AB plus BC plus CA. Okay. So now in order to verify that, you have to give all the inputs, that is 0, 0, 0, 0, 0, 1, everything. So for some of the combinations, if you check, for example, I am checking for 0 to 5 and I am not checking the inputs from 6 and 7. So there might be a problem in the code. So if I am giving the inputs as 110 and 111, so there might be a debug in the code. So I may not get the correct output for that particular inputs. So even though you have checked the 5 inputs, and if you are getting the correct result means, so your code is not 100% fit. Why? Because you may get the problem when you do the inputs 110 and 111. That is the problem. Okay. So in order to overcome this, okay, so what we should do is that, so we have to check each and every input. Okay. So if there are 1000 inputs, means the number of input combinations will be 2 to the power of 1000. So you cannot do that. So for this, there are different verification techniques like assertion-based verification, and the next one is the formal verification. Means, so whatever the synthesis file you are getting, okay, so this synthesis file you will be compared with the golden file. So there will be a golden file. So how the exact netlist should be there. Okay, you have to compare these two, and we have to see whether you are getting what the netlist you are getting is also correct or not. Okay. So there are different techniques. Okay. So all these techniques were supported by the Verilog HDL and the VHDL. So especially the Verilog HDL. Okay. And moreover, by using the Verilog HDL, so you can get the very high speed, as well as so you can get the critical paths values easily. So based on the critical path value, so you can alter the designs, and also you can go for the hardware software code design, so where you can combine your software as well as the hardware. So for this, there are some system level languages like System C and Spec C. Okay. So all these will be done by the HDL. Okay. So and one more important thing is that as per the needs of the industry, there the people who knows VHDL are not there, not existing. So in order to overcome that, there are some softwares. Okay, if you take, there are some softwares, so that directly skip the writing of this HDL program. So in the Mentor graphics software, so you have HDL designer. In the HDL designer, what is this? So if you write the truth table, means automatically it will use your VHDL code or Verilog code. So if you are using truth flowchart, if you draw the flowchart, means automatically from the flowchart you will be getting the VHDL or Verilog code. Why? Because the people who knows of writing the optimized code are very less. Okay, so that is the reason why many of the companies are coming with the software tools to develop the or to get the VHDL code or Verilog code automatically. So even Zealand is there one company. So what is this is that so it will directly generate VHDL or Verilog code from the C language. Okay. So like this, there are different softwares. So how the basics of a digital design using HDL. Okay. So first, what is this? Here we are having the circuit under test here. So it is the circuit under test. Okay, so it is the design what you have written. So after that, we have to give the inputs. Okay, so generating inputs to the CUD. So we have to generate the inputs for the circuit under test. So circuit under test means the design we have written. Okay, so and we have, after giving the inputs, we have to simulate that. After simulating, you will get the outputs. So now we have to check whether the outputs what you got are correct or wrong. So this process of, okay, the process of generating the inputs and checking the outputs will be done by using the test bench. Okay, so will be done by using the test bench. So that means, so in order to design a system, digital system by using HDL means, so we have to write two types of programs. One is the program, HDL program for the circuit under design. Okay, and the second one is this corresponding test bench. So in the circuit under design, we will describe the behavior or architecture of the circuit. In the test bench, we will give the required stimulus to your circuit under test. So these are the two types of programs we have to write when we want to design and simulate a digital system. So the main important thing is module. Okay, so now we have entered into the Verilog programming. So if you want to design a Verilog programming, so the Verilog program will start from the module to end module. So you can see here. So the first line in a Verilog program is module, and the last line in the Verilog program is end module. So in between that, we have to write your program. Okay. So in case of VHDL, what happens? In case of VHDL, first we will describe the library. So after the library, we will describe the entity. So in the entity, we will the inputs and outputs will be defined. After that, we will define the architecture. But in case of Verilog HDL, so whatever the program which we want to define, the everything is in between the module and the end module. So if you see the syntax here, module name here. So this module name can be anything. So you can keep anything as the module name, but so this module name should specify the program which for what you are writing. So the module name should be an identifier, and this identifier should specify the program for what you are writing. For example, if you are writing the program for adder mix, you can use module adder. Okay. So if you are using module, if you are using the your name mix, it will not, it is correct also. So module, if you are using module engineering for the same program adder, it is correct only, but whenever other person will see that program means, he cannot understand what is engineering. So if you use adder means, so you can understand. So this person has written the program for the adder like that. So module name. So this module name should be the identifier, but it should not be a keyword. So there is a difference between identifier and keyword. So keywords have the specific meaning in a programming language. So whereas identifier is other than keyword, anything is the identifier, but this identifier has the rules. The rules of identifier are that you can use alphabets as well as you can use the numerics, but the starting word the starting letter should not be a digit or underscore. Okay, for writing a proper identifier, you can use alphanumerics, and also you can use the underscore, but the starting letter in the identifier should not be a underscore, or it should not be a numeric. Okay, so the next one is port list. So port list means, so here you can specify the inputs and outputs. So whatever the inputs and outputs are there, so these you can specify here. Okay, whatever the list of inputs and outputs that you are using in your design should be specified in the port list. So that thing may be you can first specify the inputs, after that outputs, or else you specify the outputs, after that the inputs, but don't jumble that. But when you are coming to the predefined gates, primitives, what I told, if you are coming to the predefined gates means, so in the predefined gates, the first thing we have should be the outputs, then followed by the inputs. Okay, the next one is port declarations. In the port declarations, in the port list here, what you will do, you will just specify the names, that's all. in the port declarations, you will specify what kind of port it is, what kind of port it is. That is, the input ports or the output ports or the input ports. Okay. For the input variables, so specify that variables as input. For the output variables, specify that port as output. Okay. So the next one is include directives. So these are optional. So after that, so depending upon the type of programming, so that is type of modeling. So this internal structure, body structure will be varied. So after this end module, so everything here should be in the lower letters. So if you are using the higher case, means you will get the error during the simulation. Verilog is case sensitive, and everything what you write should be the lower case. Every sentence in the Verilog should end with a semicolon. Okay. So every sentence, every line in the Verilog should end with a semicolon, but the end module should not be ended with a semicolon. Okay. So every line in the Verilog should be closed with a semicolon, but the end module should not be closed with the semicolon. And moreover, there should not be any space between the end and module. Okay. So these two should be combined. And here, so name of the module, as I told you, and next one is comments here. Okay. So before the writing of the module, you can use the comments. Okay. So why the comments are used means, in order to make the importance of the program, or in order to make the users or the other persons who sees your program to know what about you are writing the program. So in order to know them easily, so we have to write the comments. For example, I have written the adder program. In the comment, you can write it as Verilog program for the adder. So once the other person will see that, automatically understand that it is a Verilog program for the adder circuit. So these comments can be written in the single line or multiple lines. So if we are using the single line comment, means so /2 back is the single line comment, and these are the symbols for the block comment. So this is the description of a module here. So these are the comments here. So all these are the comments. So these comments will not read by the simulator. So when you are going for the checking of the syntax or the simulator, so the software will not read these comments. So whatever there in the comments, so the software will not look into it. So you can see the port list here. Okay. So here there is you can see here it is the ALU program they are writing. So module ALU. Okay. So ALU. So ALU is a valid identifier. The problem is that they have used the capital letter. It should not be there. So module ALU. Okay. So next, first they have specified result equal Cout. So result Cout equal. So first they have specified the outputs. After that, they have specified the inputs: in1, in2, op select, mode, cin. So module name, port list. So first they have specified the output ports, result equal and Cout. After they have specified the inputs: in1, in2, operational select, mode, cin. Okay. So after specifying that, the next here we know. So based on the circuit, we know what are the inputs and what are the outputs, but the program doesn't know what are the inputs and what are the outputs. Now again we have to specify it. Okay. Here result is the output. So output. Okay. So output is the definition for giving the output port. So output size is 3 down to 0 means, so the result is a 4-bit variable. So the result is a 4-bit variable. So Cout, output Cout. Okay. So that means, so Cout is a single bit variable. So output equal. So output equal. Similarly, in1 and in2 are the inputs, and operation select is the one more input whose size is 3 down to 0. So therefore input 3 down to 0. So that means, so whatever the input you are giving will be from in1 of 3, in1 of 2, in1 of 1, in1 of 0. So this is how you specify the sizes of your inputs, and after that cin is one more input. It is a single variable. So input Cin. So mode is a single variable input mode. So like this, we have to specify the inputs and outputs. So first we have to define the port list. After that, we have to specify the port declaration. So which type of input it is, whether output port or input port or in-out port. Okay. So this is about the module interfacing. So how you can define the module. Okay. So let us. So actually, I would have taken some 15 to 20 minutes more. So here the power is not there. Okay. Uh, so I hand
Uh,
over the session to Suresh.
sir, excuse me, sir.
Please.
Sir, can I get the recording of today's session, sir? Actually,
So,
due to some network issues, I joined 20 minutes late.
okay.
Can I get the recording of this session, sir?
Yeah. So so in a day or two, so we will upload this in the YouTube. Okay. So you can
Okay,
download
sir.
it from there.
Okay. Thank you so much, sir.
Okay.
Okay, is there any questions? Okay, is there any questions? From participations, you have any questions?
Yeah, okay. Today's session is closed. Okay. Tomorrow same time we'll start this session.